We've seen a lot about the theoretical aspects, the mathematical aspects of ordinary differential equations, and now we approach the numerical approximation of ordinary differential equations. In this video, we will assume a broader perspective onto numerical methods for ordinary differential equations, in particular for the Cauchy problem, and then we will focus on the Euler method, which is the most prominent and most important example for numerical methods in the context of ODEs. So just to get a general idea of what we're dealing with, let's suppose that we generally have the Cauchy problem. U prime of t is equal f of t and u of t. And we have the initial condition u of t naught is equal u naught. The key ideas of the numerical analysis of ordinary differential equations is the following. So what we generally know is u naught, the initial condition at time t naught, and we know f. Both of these are typically known only up to measurement errors. However, finding the exact solution typically is not feasible. So there are many ordinary differential equations for which we cannot find an explicit formula for the solution, even though we know that the solution exists, at least for some time, or maybe for all time, but we do not have an explicit solution formula. And even if maybe the data of the problem are subject to measurement errors. So we can only find a solution perhaps approximately, which means that we want to approximate the value u of t for some time t after t naught by a computational method. So the underlying problem is that we want to know an approximation for u of t for some time t after the initial condition. Maybe we are only interested in knowing the solution after some fixed time t. Maybe we have a physical process and we want to know where's that physical process after maybe 10 seconds. Or more commonly, we are interested in the development of the physical process at certain snapshots, at certain time intervals. So typically we have set points in time, t0, t1, t2, and so on, and we approximate by a numerical method u of t0, u of t1, u of t2. And just to give you an idea of what it looks like, let's take a look at an example. What we see here is a numerical approximation for the solution of the following initial value problem. Namely, we've got the initial condition u0 equal 1, and the ordinary differential equation u prime of t is equal minus 2 times u of t minus exponential of minus 4 times t plus 2. So as you can tell, this is a linear differential equation. The Cauchy problem, it's non-autonomous and inhomogeneous. You should check what it means and verify it by yourself as an exercise. And what you see here is, on the one hand, the orange curve, which is the solution to that ordinary differential equation, graphed from time t equals 0 up to time t equals 1. And the blue curve is a numerical approximation, of that. And that approximation is obtained from the Euler method. And we start at t equals 0. And as you can tell on the left, there the two graphs agree. And then the Euler method goes a straight line up to time t equals 1 over 8. Then we change the slope again, go up to time t equal 2 over 8. We again change the slope and draw a line now up to time t equals 3 over 8. Then we see that the slope is suddenly positive, and we keep drawing a line up to t equal 1/2, and so on. In fact, there's the graph looks very flat on the blue curve, even though it's actually a bit bent. So what the numerical approximation for our ordinary differential equation looks like typically is a polygonal line consisting of linear segments. You can think of it like we draw a line over for some time t with a fixed slope, then we change the slope again, keep drawing the line, change the slope again, keep drawing the line, change the slope again, keep drawing the line, and so on. Now in this example, we have partitioned the interval from 0 to 1 into 8 subintervals, and the blue curve here, the numerical approximation, stays constant, has a constant slope over each of the subintervals. The basic idea is that the shorter we pick the subintervals, the more subintervals we pick, the better will be the approximation. Now here we have the graph of the solution together with, again, a numerical approximation, again the blue line, but this time the length of the subintervals is not 1 over 8, but 1 over 16. And what you can tell is that the blue curve now gives a much better approximation of the orange curve. Now we decrease the length of the subintervals even further, and every subinterval is now length 1 over 32. Now it's 1 over 64. And you can tell that the blue curve, the approximation, is closing in on the orange curve. I've halved the length of the subintervals again. This time it is 1 over 128. So bringing that in line with our idea of what it means to approximate the solution for an ordinary differential equation, for a Cauchy problem in particular. Typically, we're interested in observing the solution over some fixed time interval from the starting point t0 up to some final time. And then we partition this time interval into smaller and smaller subintervals. In the most simple case, all these subintervals have the same length. And what we do is we number the boundaries between the subintervals. We have at the very beginning t0, then the next boundary between subintervals is t1, then the boundary of the next subinterval is t2, and so on. So in particular, the distance of t0, t1, t2, etc. is always the length of the subintervals. And then we try to approximate the function u at the boundary between the subintervals. And then typically we interpolate between these approximations. For example, linear interpolation. Of course, much of what I've just said can be changed in more advanced methods. There's lots of flexibility of what you can do, of course. But this is the most basic outset. Okay, so how do we actually find the approximations? Now, typically, if you've got an approximation for u at t0, in fact, it's typically is known exactly, then we use that information to find an approximation for u at time t1. Then with these two approximations, we approximate u at time t2, and so on and so on. So basically the next approximation at time tk plus 1 is calculated from the information that we already have from the previous approximations. In fact, for the most common numerical methods, in order to approximate, for example, u at time tk plus 1, we only use the approximation of u at time tk. But there are also so-called multi-step methods where we go further back in time to find the next approximation. And as usual, as a numerical analysis, there's a trade-off between the computational effort and the accuracy of the method and the simplicity of the method. For example, it is easy to find numerical examples where, in order to get an accurate numerical approximation using the Euler method, then we need lots of computational effort. And These problems have led to a large zoo of different numerical methods. Okay, let's get to the Euler method. And we only start with the algorithm for the time being. There are different ways to introduce the Euler method. We start with an introduction to the Euler method that uses difference quotients. So let us assume that we have got a differential equation, a Cauchy problem. U prime of t is equal f of t, u of t, together with the initial condition u of t naught is equal u naught. Let us suppose this differential equation has a solution defined for all times, mapping into r to the n. Let's call the solution u. And okay, let us suppose that we already know u of t exactly, or perhaps approximately, and we want to approximate u at a later time, u of t plus h. Okay, in order to derive such an approximation, for any time t at any step size h, any positive step size h, we recall the following approximation of the derivative of u, namely u of t plus h minus u of t divided by h, which is the difference quotient, can be seen as an approximation of u prime at t. Okay, if we rearrange this approximation, then we see that u of t plus h is roughly the same as u of t plus h times u prime of t. Okay, and now using the differential equation, we get that u of t plus h is roughly the same as u of t plus h times f of t and u of t. We notice that this last approximation does not mention the derivative of u explicitly anymore. This approximation only works with the step size h, the time t, and the value u of t. Now, there's a different way to derive the Euler method. Namely, we also recall that if we have this time t and the step size h, then u of t plus h is exactly the same as u of t plus the integral from t up to th of the derivative u prime of s ds. Now, for h small, we can reasonably approximate the integral by h times u prime at the left endpoint of the interval. This is just a Riemann sum, a very simple Riemann sum. So we get the approximation u of t plus h is roughly the same as u of t plus h times u prime of t. The same as before, and again, using the differential equation, what we get is that u of t plus h is approximately u of t plus h times f of t u of t. Again, the same approximation of u of t plus h, this time with integrals instead of difference quotients. And finally, we can also use a Taylor series. Namely, again, for any time t and any positive step size h, we have the approximation theorem of Taylor, which tells us that u of t plus h is exactly u of t plus h times u prime of t plus h squared over 2 times u prime prime of xi. That xi is somewhere in the interval from t up to t plus h. For very small h, we can then hope that the last term is negable. And so again, we have the approximation u of t plus h is roughly the same as u of t plus h times u prime of t. And again, using the differential equation, we get that u of t plus h is roughly the same as u of t plus h times f of t u of t. Okay, with that formula, we can derive an iterative algorithm to approximate the solution u at successive times. Okay, more concretely, suppose we start at time t naught, and we already know u at time t naught from the initial condition. what we're going to do is we approximate u at time t1, which is just t0 plus h. Then we go one step size h further and approximate u at t2, which is t0 plus 2 times h, and so on and so on. For example, time t3 would be t0 plus 3 times h, and generally we define time tk as t0 plus k times h. So we have a succession of points in time, t0, t1, t2, and so on, taking steps of size h. And at each of those points in time, we compute approximations of u at those points in time. So we already know u0, which is u at t0. It's just the initial condition. We know that one exactly. And next, we're going to approximate u at time t1 by some value u1. Then u2 is an approximation of u at time t2. u3 is going to be an approximation of u at time t3. And generally, uk is going to be an approximation of u at time tk. And we find these approximations uk using this recursive formula that we have found on the previous slide, namely uk plus 1, which is an approximation of u at time tk plus 1, is defined as uk plus h times f at time tk uk. So concretely, we start with u0, which is already known. It's exactly u at time t0. And we compute. u1 is equal u0 plus h times f of t0 u0. u2 is equal u1 plus h times f of t1 u1, and so on. For example, u3 is equal u2 plus h times f of t2 u2, etc., etc. And generally, uk plus 1 is defined as uk plus h times f at time tk and uk. So we start with the initial value, and then we compute approximations of u at time t1, t2, t3, successively using this recursive formula here. We use the approximation at time tk to get another approximation at time tk plus 1. Okay, let's take a look at an example, namely the Cauchy problem. U prime of t is equal ut, and we have some initial condition u0. Then we compute u1 is equal u0 plus h times u0, because f of tu is just u. It's very simple in this case. u2 is equal u1 plus h times u1. u3 is equal u2 plus h times u2, etc. uk plus 1 is equal uk plus h times uk. Slightly more complicated. We have the Cauchy problem. U prime of t is equal 3 times u of t plus sine of t squared. We can just plug in the formula. This time the system is non-autonomous. And we compute u0, which is already known, so we already have that value to start with. Then we compute u1 equal u0 plus h times f of tu at 0, at index 0, which is 3 u0 plus sine of t0 square. Now u2 is equal u1 plus h times 3 u1 plus sine of t1 square. And u3 is equal u2 plus h times 3 u2 plus sine of t2 square, etc., etc. And uk plus 1 is equal uk plus h times 3 times uk plus sine of tk square. Yet another example. Suppose we have the differential equation u prime of t is equal u of t square. Okay, we start with u0. Then u1 is equal u0 plus h times u0 square. u2 is equal u1 plus h times u1 square.
u3 is equal u2 plus h times u2 square, and so on. Eventually, uk plus 1 is equal uk plus h times uk square. Let's have a look at a slightly more complicated differential equation. U prime of t is equal -2 times u of t minus exponential of minus 4t plus 2. Okay, we start with initial condition u naught, and we compute u1 is equal u naught plus h times -2 u naught minus exponential of minus 4 t naught plus 2. Now u2 is equal u1 plus h times -2 u1 minus exponential of minus 4 t1 plus 2. And generally, uk plus 1 is equal uk plus h times -2 uk minus exponential of minus 4 tk plus 2. Okay, let's also have a look at another Cauchy problem where the right-hand side might not be defined for all values of t and u. Okay, we can still apply the Euler method. Whether that's a smart thing to do or not is a different question, but still we can do that. Let's take a look at the Cauchy problem. U prime of t is equal 1 over 3 minus t times 2 minus u of t. So we start with u naught, the initial condition, and we compute u1 is equal u naught plus the fraction h over 3 minus t naught times 2 minus u naught. u2 is equal u1 plus h over 3 minus t1 times 2 minus u1. And u3 is equal u2 plus h over 3 minus t2 times 2 minus u2, etc. Eventually, uk plus 1 is equal uk plus h over 3 minus tk times 2 minus uk.
Now, to finish this presentation, I would like to show you a small movie, namely, we have lots of approximation of the logistic differential equation for different step sizes using the Euler method. So let's suppose we have the logistic differential equation u prime of t equal 3 times 1 minus u of t times u of t, with initial condition u at 0 is equal 0.01. The first approximation is a straight line. Then quickly you see that the approximation roughly assumes the form of the solution of the logistic differential equation. For small step sizes, the approximation is a bit rough and the behavior looks a bit erratic. But as the step sizes go down, for example at 1 over 25, we already have quite a passable approximation. At about h equal 1 over 50, the graph has no visible changes anymore. It is a very fine resolution of the interval from 0 to 1. How small you want to choose the step size, of course, depends very much on the application.